students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, we are going to discuss the moment generating function and the cumulative generating function of Gaussian distribution, and how to calculate skewness and kurtosis of Gaussian distribution with the help of MGF and CGF. Now, the introduction of Gaussian approach towards machine learning is given in the last lecture, um, which is very important in dimensionality reduction and also in solving nonlinear regression problems related to machine learning. And let us recap or recall the definition of the density function of Gaussian distribution. The density function of a Gaussian distribution, of course, which is widely known as the normal distribution, is given by 1 bar sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square, and where the x is a variable which varies from minus infinity to infinity. That means x is any real lying between minus infinity to plus infinity, and mu comma sigma are parameters, and these here mu is also any real number, but sigma is strictly greater than 0, that is a positive, a non-negative number. So this a random variate which follows this, which have this density function, is known as the Gaussian distribution or normal distribution. Okay, and we also verified in the last class that the mean is mu and the variance is sigma square of the Gaussian distribution. Also, we have derived the moment generating function of the Gaussian distribution. That is, we have also discussed the moment generating function of the Gaussian distribution, that is e power mu t plus sigma square t square by 2. Okay, now let us look into the other details of Gaussian distribution. Of course, these are the things which you must have a small knowledge, like pi is a constant. It's an irrational number, well-known irrational number, and E is also a famous irrational number. And the mean of normal distribution is mu, and the variance is sigma square. Standard deviation is sigma, and the distribution whose density function is 1 by sigma root 2 pi e power minus 1 by 2 x minus mu whole square by sigma whole square is called normal distribution, denoted by n of mu comma sigma square. Of course, we discussed the properties of normal curve, which is reverse bell shaped, and it is equally symmetric about the line x is equal to mu, and the mean, median, mode, all the three will coincide, and the 68% of the area will be fluctuating between mu minus sigma and mu plus sigma. 95% of the area will be lying between mu minus 2 sigma and mu plus 2 sigma, and 99%, that is almost all the area under normal curve, will lie between mu minus 3 sigma and mu plus sigma. Also, we have proven that total area under normal curve is unity. Also, we also discussed the property that x-axis is an asymptote of the normal curve, and the points of inflection are mu minus sigma and mu plus sigma. That is, the concavity becomes convexity and the convexity becomes concavity. These things we have discussed in the last lecture. Now, apart from this, we also discussed what is a standard normal. Simple. The standard normal variate is derived from the original general normal variable. That is, suppose let us consider the density function of the normal distribution 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square. And suppose we replace x minus mu by sigma with z, then automatically we'll get a new function which can be denoted by phi of z or phi of z, which becomes 1 by root 2 pi e power minus z square by 2. Because when we substitute this by applying expectation on both sides, that is expectation on both sides, we observe that the mean, that is E of Z, will be 0. And by applying the variance on both sides, we could observe that the variance of Z will be 1. Let us see that. Let us apply expectation on both sides, that is E of x minus mu by sigma. E of Z is equal to E of x minus mu by sigma. That is equal to E of x minus E of mu. E of mu means E of constant. Expectation of a constant is always constant. That is why we get mu by the constant sigma. But E of x, as we just discussed in the previous slide, E of x is equal to mu for a normal distribution. So, which is nothing but mu minus mu by sigma, and hence we'll get 0. Now, we are going to prove that V of Z will be 1. Now, we are going to prove that V of Z is 1. That is why we are considering V of Z, which is V of x minus mu by sigma. Being the constant, sigma being the constant, and when it comes out the variance, it becomes square. We have a property which you come across in your probability and statistics in your second semester curriculum. In that, you have come across this property. When a constant comes out of the variance, it becomes the square, and V of x minus V of mu. Now, 1 by sigma square. Just now, we had the formula V of x. The variance of normal distribution is sigma square, and variance of a constant is always 0. This is also a property which you learned in your second semester. So, variance of constant is 0, and variance of x is sigma square, that is 1. So, obviously, this function will be turned into this function, which is famously called as the standard normal variate. Okay, so let us summarize these things. So, in general, normal distribution is represented with the function 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square. But we have a special normal distribution where whose standard deviation is 1 and mean is 0, and hence it becomes 1 by root 2 pi e power minus z squared by 2. Now, your doubt is, what is the need of having this special normal distribution? Why we are considering whenever mu, for each pair of mu and sigma will have a normal distribution. So, what is the specialty of this particular pair? Mu is equal to 0 and sigma is equal to 1. Let us explain it in a easy way. Let us take the example of logarithm tables. In our elementary school level, we used to have logarithms: log base 2, log base 3, log base 4, log base 10, log base e. So many logarithms. For each and every real number, each and every non-negative real number, we can have a logarithm. That means we need separate tables for separate logarithm. That means we need a separate table for log base 2, we need a separate table for log base 3, log base 4, log base 10, like that. So for any problem, for each and every different problem having different logarithms, we need different tables. That is a Herculean task. That is why we used to convert every logarithm into log base e. We used to convert every logarithm into log base e. Okay, that means natural logarithm. This is called natural logarithm. We have only two tables, log base e and log base 10. By using these two tables, we can calculate log base 2 or log base 3, whatever we require. How? Let us explain it with a simple example. Suppose you need to calculate log 7 base 3, but we know only log 7 base e because we have only one table, log base e table. Then we'll convert this into log 7 base e into log e base 3, and we can find this value and this value from the log e table, and we can use and we can find this value. So that is why we have created a natural logarithm, and with the help of natural logarithm, we used to calculate any logarithm in our elementary level. In the same way, as we are having 1 minute. In the same way, as we are having infinite normal distributions, because whenever we select a pair mu and sigma, we get a new normal distribution. Okay, so we have infinite normal distributions. So we are, for all of them, we are having a single normal table, which is called standard normal table. We'll convert every normal distribution into standard normal variate, and we use this table to calculate the probabilities. That is the importance of standard normal variate. Okay, now here we are seeing the standard normal distribution curve, which is centered about x is equal to 0, mean is equal to 0, which is symmetric on both sides, and remaining themes you can understand from the previous discussion. And this is the standard normal table. Actually, this is nothing but, this table value is nothing but calculated from the integration of e power minus z square by 2 dz divided by root 2 pi. Okay, and all these values are framed into a single table. Suppose this is 0 to 2, you will get pi of 2. If you put 2.37, you will get pi of 2.37. All these values are represented in this table. Okay, now by using this table, we can calculate the probabilities very easily. Let us see how to check out a table value from this table. I'll give you an example. Of course, I have discussed it in the last lecture, but let us repeat it once again. So, if we want a table value 2.37, or let us, because it is 1.37, okay, then we have to partition it into two parts, 1.3 and 7, 1.3, 7, and we have to search 1.3 in the rows, that is here, and we have to search the 7 in the columns. 1.3 will be marked in the rows, 7 will be marked in the columns, and both will be meeting at this number, which is 0.39796. That is the table value. So A of 1.37 is 0.3979. Okay, now I'll explain one more small example, then we'll go to the problems. Suppose you need to check 1.1. Okay, then you'll write it A of 1.10, because we need at least two digits, and you will take 1.1 as first part and 0 as second. You will search 1.1 in the rows, that is here, and 0 in the column, that is here. Both are meeting at this number. So the table value will be 0.3644. So in this way, we try to locate the table values from the standard normal table. Now, we are heading towards some applications of normal distribution. Before going to the applications, I'd like to suggest three important formulas. Let us look into those aspects. First, in the real time, when we are supposed to calculate, suppose we might be supposed to calculate three kinds of probabilities. The first is the probability of India scoring runs between 300 to 350. What is the probability that India will score a total between 300 to 350 in the test match or one day match? What is the probability? And second one is, what is the probability that India will score more than 250 runs in an innings? And third one is, what is the probability that India will be all out within less than 200 score? That means India will be bowled out a score less than 200 runs. So there are three kinds of whether it is a score or marks or whether it is kgs or weights, heights, whatever the random variable, you can measure what is the probability that a student is going to have a height between 5.5 inches to 6.5 inches. What is the probability that a student will have weight of 65 kg, more than 65 kgs? What is the probability that yield of a crop is less than 500 kgs? Like that, in different situations, like whether it is heights or weights, okay, or scores or marks, whatever, there will be three. We can categorize them into three different situations. That is, probability of random variable falling between two limits, probability of a random variable exceeding a limit, probability of a random variable confining to a limit. See, x lying between two numbers, x greater than a number, x less than a number. Okay, x lying between two numbers, x greater than a number, x less than a number. That means x falling between two limits, x exceeding one limit, x is confined to one limit. So in the three different cases, we are going to have three different approaches. Let us discuss those things. First, let us start with the first instance. So here we'll have two situations. That is, when these numbers are positive, that is probability of alpha less than or equal to x less than or equal to beta. Okay, suppose alpha comma beta are of same sign, then we write the formula. We'll use a different formula, and if alpha beta are of opposite sign, we will use a different formula. When alpha beta are of same sign, that means like p of 2 less than or equal to x less than or equal to, I'm writing here p of 2 less than or equal to x less than or equal to 3. Okay, here 2 and 3 are both positive, same sign. Then the formula will be a of upper limit, area under upper limit, minus area of under lower limit under modulus. That is upper limit area minus lower limit area within modulus. That is a of 3 minus a of 2 within the modulus. Taking absolute. And when the signs are opposite, that is when we have minus 2 less than x less than 3. You see, this is a negative number and this is a positive number. Then we'll use a formula area of upper limit plus area of lower limit. Okay, that means when the signs are opposite, we have to add the areas, upper limit area and lower limit. When the signs are same, we have to subtract areas, upper limit area minus lower limit. And in both the cases, we have to apply modulus to make the area, because area is always positive, we have to make the number positive. That is why we have to apply modulus. Okay, and also we have to understand that because the formula a of z is 1 by root 2 pi, integration of 1 by root 2 pi e power minus z square by 2. Okay, and this is even function. A of minus z is always equals to a of plus z. That is, being an even function, being the area a of z is an even function, there is no differentiation between a of minus z and a of z. Like cos minus theta and cos theta, both are equal because cos is even function. That in the same way, this is even function. That is why a of minus x will be a of plus x. Okay, now let us come to the second instance, that is p of x greater than or equal to a number. Okay, like x greater than or equal to x1. So here also we divide the thing into two cases. Case 1, when x1 is positive and x1 is negative. That is, example, if India scores more than 250 runs, probability of India scoring less than 200 runs. Oh, negative, sorry. P of India x exceeding minus 250. You can understand. See here, 250 is positive. Here, minus 250 is negative. Then the formula will be half plus area of the limit under modulus. Here, the formula will be, sorry, here the formula will be half minus area, here the formula will be half plus area. Okay, so when the limit is positive, the number is positive, we have to subtract the area from half. And when the limit is negative, we have to add the area to half. Why? Why we are using this formula? You might be surprised. Let me explain the help of diagrams. See, you know the area under normal curve is unity. That is, this is half, this is half. And suppose if this x1 is positive because this is 0, you can understand this is z1. Z1 is positive, and you want to calculate p of z greater than or equal to z1. That means you have to calculate this area. This area you have to calculate. That means the total area is, what is the total area? This is half. And you have to subtract this piece, this area from half, you will get this area. To get this area, in order to get this area, you have to subtract this piece of area from the total area. That is half minus area of z1. Half minus a of z1. Okay. Now let us consider the second case. That is when z1 is negative. Suppose we need to calculate z1, and we need to calculate p of z greater than or equal to z1, where z1 is negative. That is left side of origin. Z greater than or equal to z1 means we have to calculate this shaded area. This shaded area we have to calculate. And we know that this is half because total area is unity. This is half, this is half. And this will be a of z1. So total shaded area will be half acre plus this area. That is why 0.5 plus a of z1. Okay. In this way, we will respond to the second case. Okay. And for third instance, that is p of z less than or equal to z1, we need not to use any formula. Just we will convert it to the second case by using the complementary formula. Z less than or equal to z1 is equal to 1 minus z greater than or equal to z1. Okay, this is a complementary property, and we can convert this into greater than, and we can use the second case formula. Now, after discussing this, we are going to solve a problem. So, let us consider a problem. Yes. See, here x is a random variable representing the length of time. It has a mean of 50 and a standard deviation of 15. We have to find the probability that x is between 50 and 70. The moment generating function definition is given by mxt is equal to expectation of e power tx. Okay, and here our f of x is given by 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square. So let us calculate the moment generating function of the normal distribution. So mxt is equal to e of expectation of e power tx, that is equal to integral minus infinity to infinity e power tx f of x dx, that is equal to 1 by sigma root 2 pi integral minus infinity to infinity e power tx e power minus 1 by 2 x minus mu by sigma whole square dx. Okay, so we arrived at this step. Expectation of e power tx is equal to 1 by sigma root 2 pi integral minus infinity to infinity e power tx e power minus 1 by 2 x minus mu by sigma whole square dx. Now, as bases are equal, we can add the powers, that is 1 by sigma root 2 pi integral minus infinity to infinity e power tx minus x minus mu by sigma whole square into 1 by dx. And by expanding it and by making some mathematical manipulations, we arrive at the step 1 by sigma root 2 pi integral minus infinity to infinity e power mu square t square by 2 mu square t square by 2 and e power minus 1 by 2 x minus mu by sigma whole square. Okay. We when we calculate this 1 by sigma root 2 pi integral minus infinity to infinity e power tx e power minus 1 by 2 x minus mu by sigma whole square, and we arrive at the step 1 by sigma root 2 pi minus infinity to infinity e power mu t plus sigma square t square by 2 into e power minus 1 by 2 x minus mu by sigma whole square into dx. You can expand a minus b whole square, and you can, by adding some deletions and additions, you will arrive at this step. Clearly here the variable is x and this is constant. You can write it as outside, that is 1 by sigma root 2 pi e power mu t plus sigma square t square by 2 minus infinity to infinity e power minus 1 by 2 x minus mu by sigma whole square dx. Okay, so we have to calculate this integral. Let us calculate this integral separately. The integration is integral minus infinity to infinity e power minus 1 by 2 x minus mu by sigma whole square dx. Let us substitute x minus mu by sigma with z. Let us replace x minus mu by sigma with z. Then dx will be equals to sigma dz. And this becomes integral minus infinity to infinity e power minus z square by 2 sigma dz. Okay. By substituting this in the previous calculation, we get 1 by sigma root 2 pi e power mu t sigma plus sigma square t square by 2 integral minus infinity to infinity e power minus z square by 2 sigma dz. Sigma sigma will be cancelled. Okay, and we arrive at this step. And we have a formula for this integral, for this definite integral from the gamma functions, that is 1 by root 2 pi e power mu t plus sigma square t square by 2. The integral becomes root pi root 2 pi, and root 2 pi will be cancelled. The final answer is e power mu t plus sigma square t square by 2, and hence we get the MGF. The MGF of the normal distribution is e power mu t plus sigma square t square by 2. Similarly, we can observe that the standard normal variate will have moment generating function e power minus z square by 2. Okay, so these are the moment generating functions of general normal variate and standard normal variate, which you could see here. This is the standard normal variate. You can use the same integration techniques which I have discussed now to establish this fact that moment generating function of a standard normal variate is e power t square. And by using that, we could also prove that the general normal variate, the moment generating function, by using this replacement, we will get that e power mu t into e power sigma square t square by 2. Now, we are going to see the cumulant generating function of normal distribution. Cumulant generating function of normal distribution. So, let us consider the moment generating function of the normal distribution, that is e power mu t plus sigma square t square by 2. Now, cumulant generating function is nothing but logarithm of moment generating function. So, apply log on both sides. Applying log on both sides, we'll get log of mxt log of e power mu t plus sigma square t square by 2. Okay. And log e base e, that means these will be cancelled. You will get mu t plus sigma square t square by 2. So the cumulant generating function of normal distribution is given by, it is denoted by kx of t, which is logarithm of moment generating function, that is given by mu t sigma square t square by 2. So by summarizing this, we'll understand that the moment generating function of a normal distribution is e power mu t plus sigma square t square by 2, and moment generating function of standard distribution is e power minus t square by 2, and the cumulant generating function of normal distribution is mu t plus sigma square t square by 2. Okay, now with the help of cumulants, we are going to calculate the skewness and kurtosis of a normal distribution. Let us recap what is skewness. Skewness is a measure of symmetry of a distribution, probability distribution or data set, which is nothing but whether the distribution is symmetric about the mean, or whether it is slightly stretched towards the right or slightly stretched towards the left. This is called perfectly symmetric distribution. This is called positively skewed. This is called negatively skewed. Okay, and we have a formula to calculate skewness. The formula is given by the Paul Pearson as beta 1. Beta 1 is the measure of skewness, which is given by mu 3 square by mu 2 cube. Mu 3 square by mu 2 cube. So, the measure of skewness is nothing but the ratio of third moment square by second moment cube. Okay, and here you can see the perfectly symmetric distribution where the mean, median, mode will be coincided and it is equally stretched on either side of the mean. And here you can see the positively skewed distribution, which is stretched right towards left towards the mean, and negatively skewed, which is more stretched towards the mean right side. Okay, these are the three graphs of skewed distribution, that is perfectly symmetric, positively skewed, and negatively skewed. If beta 1 is 0, then we call symmetric distribution. If beta 1 is greater than 0, we call it as positively skewed distribution. If beta 1 less than 0, we call it as negatively skewed distribution. And kurtosis is a measure of bulginess of the curve. That is, sometimes the curve may be balanced, sometimes the curve may be highly peaked, that sometimes the curve may be very flat. Okay, so balanced it is called mesokurtic, highly peaked is called leptokurtic, which is very flat is called platykurtic. Okay, so to measure the kurtosis, that is the bulginess or the extension of the curve, we need a measure which is given by Paul Pearson as B2 mu 4 by mu 2 square. That is fourth moment by second moment square. If B2 is equal to 3, we call it as mesokurtic. Then the curve will be very balanced. And if B2 greater than 3, the curve will be very highly peaked. If B2 is less than 3, then the curve will be very flat, like this, platykurtic. Okay, now we are going to calculate. So here we can see all the three things in a single diagram: leptokurtic, highly peaked; balanced, mesokurtic; very flat, platykurtic. Okay, now we are going to calculate the skewness and kurtosis for normal distribution. Before that, let us just have a look into the cumulative generating function of a distribution that is given by cumulative generating function, which is denoted by kx of t, which is logarithm of moment generating function. Logarithm of moment generating function is cumulative generating function. Okay, it is denoted by kxt. Now, here we are seeing some interesting relationships between the cumulants called k1, k2, k3, k4 and the moments mu1, mu2, mu3 and mu4, etc. These relationships you can calculate with the help of moment generating function. Okay, you can by heart them as formulae. K1 is always equals to mu1 and k2 is always equals to mu2 minus mu1 square, that is variance, and k3 is always gives you the value of mu3 minus 3 mu2 mu1 plus 2 mu1 cube. Okay, and k4 gives you the relationship between k4, mu4, mu3, mu1 and mu2, etc. So these four relations plays an important role in calculation of skewness and kurtosis. Now, our intention is to calculate the skewness and kurtosis of a normal distribution. Let us have a look into that. Suppose let us consider the moment generating function of a normal distribution, mxt, that is e power mu t plus sigma square t square by 2. Now, let us apply logarithm on both sides. Log of mxt of t, that is log of e power mu t plus sigma square t square by 2. Because log and e can be cancelled, we get mu t plus sigma square t square by 2, which can be written as mu t plus sigma square t square by 2 plus 0 t cube plus 0 t power 4 plus 0 t power 5, so on. And we know that log of mxt is denoted by the cumulative generating function, that is kx of t. Okay, so cumulative generating by kx of t is given by mu t plus sigma square t square by 2 plus 0 t cube plus 0 t power 4, etc. You know the quotient in the when this is a cumulative generating function, the quotient of t is called as the first cumulant k1. The quotient of t square is called as the second cumulant k2, and the quotient of t cube becomes the third cumulant, t4 becomes the fourth cumulant. So, what did we get? K1 is mu, which is mean. K2 is sigma square by 2, which is 2 times of variance. And K3 is 0 and K4 is 0. And now we have to calculate the skewness and kurtosis. Let us go to the formula, that is K3 is mu3 minus 3 mu2 mu1. Here I am writing K3 mu3 minus 3 mu2 mu1 plus 2 mu1 cube. Let us substitute these values. That is K3 is 0, we got mu3, we don't know, mu2 and mu1 is 0, always 0, so that is why this becomes 0 and this becomes 0. So mu3 will be 0, because always mu1 is 0. The first moment is always 0, that is why we get mu3 minus 0 plus 0, so mu3 is 0. So since mu3 is 0, we have the Pearson's skewness formula, that is mu3 square by mu2 cube, that is 0 square by mu2 cube, that is 0. B1 is 0 means the distribution, normal distribution, is perfectly symmetric. Perfectly symmetric. Okay. So what do we understand? We understood that the normal distribution is perfectly symmetric about the line x is equal to mu. X is equal, that means equally stretching on the both sides of x is equal to mu. Okay, and after this, we try to calculate the kurtosis of the normal distribution, which is given by the formula beta 2 is equal to mu 4 by mu 2 square. Mu 4 by mu 2 square. Now, we are having mu 2 is equal to mu 2 as we have 2 sigma square or k2. We can understand mu 2, we can write here mu 2 is equal to k2 plus mu 1 square, where k2 is sigma square by 2 plus mu 1 is 0, so mu 2 is equal to sigma square by 2, so you can write it as sigma square by 2. And mu 4 from this relationship mu 4, you will obtain it as 3 plus sigma square. Okay, or 3 sigma square by 2 plus some number. So by separating this, we will get 3 plus some positive quantity which is greater than, which is of course 3 plus some positive quantity which is approximately equal to 3, and hence you can declare that this is mesochaotic. Beta 2 is equal to 3, and hence this is mesochaotic. Mesochaotic means it is very balanced. Okay, so in this way you can discuss on you can find out the skewness and kurtosis of a normal distribution. Okay, so finally in this lecture we have discussed what is the MGF of a normal distribution and the cumulative generating function of normal distribution, and also we found the skewness and kurtosis of the normal distribution. Okay, we found that skewness is 0, kurtosis is exactly 3, and hence we established the fact that the normal distribution curve is perfectly symmetric, and the normal distribution curve is always mesochaotic, very balanced in the height. Okay, with this I'd like to conclude this lecture. In the next class we'll discuss about the exponential distribution, which is also an important uh, uh, part of continuous probability distributions, which plays an important role in analyzing the time series and machine learning problems. Okay, so we'll meet in the next class. Thank you for your patience. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.